Hello and welcome to the module number 1 of AIE's curriculum. Today we're going to be talking about machine learning.
Hey everyone, my name is Montej. I'm a senior here at the University of Southern California studying computer science.
I'm Ryan. I'm a sophomore here at USC and I'm studying computer engineering and computer science. As for what we'll be talking about in this module, of course this module is on machine learning, so we will start with a brief introduction to what machine learning is, the different kinds of machine learning, as well as workflows in producing machine learning models, ethics in the context of machine learning in section 4, and finally we'll be going through a notebook walkthrough for the module 1 notebook you guys should have.
So first, let's talk a little bit about what machine learning actually is. Machine learning is one of the various subsets that exists within AI. The whole goal of machine learning is to enable computers to process large amounts of data, find patterns, and just interesting features about the data sets that you want to know more about. It's used in a lot of various industries today, from the medical industry to finance and even self-driving cars, which you may have seen on the road. The main goal for this slide is to show that machine learning is just a subset of AI, and while all machine learning is AI, not all AI features and models out there can be considered machine learning.
There are multiple different kinds of machine learning techniques based on the labels that we give the model. That is, the targets that we actually give the model to aim for as it's learning to do the process we want it to do. The first and the simplest is supervised learning. Supervised learning is the process of giving labeled data to the model along with the samples of the data in the form of features. The model takes those features, tries to look for some pattern, gives an output, and then backpropagates or adjusts based on the difference between the model's output and the true label that we gave in the original data. The second kind is unsupervised, where we don't actually have these labels. In this case, the model is kind of tasked with finding its own patterns and own understanding of the data that we give it, regardless of what we actually think the data might be. In a sense, it finds its own labels for the data as opposed to us giving it labels. The third kind is reinforcement learning. Reinforcement learning is often used in game environments or for robotics, wherein given a certain scenario or a certain state, the agent, or the model in this case, takes a specific action and is given a reward or a penalty based on this action or penalty. Eventually, the model learns to maximize the reward that is given by its actions. And in doing so, Max is able to learn how to navigate and interact with its environment in the desired manner.
So the standard machine learning workflow involves 5 main steps. The first is data collection and pre-processing, where you're collecting data and then processing it to make sure that it's best fit for training. The second is extracting the main features and figuring out what exactly you want to look at when it comes to your data set. The third is probably the most important, and that's figuring out what exact model you want to use. There are a lot of machine learning models out there, but it's really important that you choose the one that's the best fit for your scenario. The fourth is making sure that your model is actually doing well, so evaluating it and optimizing it based off of the results you get. And the final step is deployment and then monitoring. For the sake of simplicity, I'm only going to talk about model selection and model evaluation, but I highly recommend that you do your own research to get some more insight into the other steps that we discussed. When it comes to model selection, there are a lot of different options out there for you to choose, but it really comes down to what type of data you're working with and what results you're interested in finding. And then based off of that, you can trial and error a few models to see which one gives you the best results. In the notebook that we'll walk through a little bit later on, we walk through a linear regression model, a decision tree, and then also a neural network. And this is done in order to give you guys a little bit more of an introduction into how to work with machine learning models and what different types of models are out there, just so that when you're implementing your own model, you'll have a little bit easier time working through it and figuring out what parameters to set. When it comes to actually training the model, this is a process that takes quite a while, but again, it depends on what type of data you're using, whether it's supervised, whether it's unsupervised, and then there's a lot of trial and error in making sure that the parameters you set, that the values you're placing in the actual function are the right ones to get the best possible result. So in order to make sure that your model is actually performing the best it can be, it's really important to evaluate and optimize it throughout. When it comes to evaluation, it's important to consider what type of work you're actually doing, whether it's classification, which is more of clustering and grouping things into similar sets, or regression, which is more numerical based analysis. And then based off that, you can figure out what type of metrics you can use in order to figure out how well your model is doing. In our notebook, we use R squared, but there are a bunch of other metrics out there that you should take a look into and evaluate your model based off of those metrics to get a holistic view of how exactly your model is performing. It's also really important to be aware of whether your model is overfitting or underfitting, which are both big issues when it comes to machine learning training. Overfitting pretty much means that your model is picking up on too much information. It's picking up on irrelevant fields and noise in general, and that's going to lead to generalizations and just predictions that aren't accurate. The other problem is being underfit, and where your model is too simple and it's not picking up on enough information, so it won't be able to give you an accurate description of what exactly your data means. It's really important that you also use cross-validation, where you check with different metrics, with different variables, and get a really nice overview of what exactly your model is performing and what areas it may lack on, just so you can improve it over time and make sure that when it's ready for deployment, it's in the best possible situation.
Privacy and security are perhaps the largest issue that face machine learning models today, as they require so much data that's often coming from sensitive fields such as medicine and finance. For example, data misuse can lead to ethical and legal violations of policies such as the GDPR, CCPA, as well as HIPAA, all policies put in place to protect human data, especially protected human data. The other issue is that machine learning models can fall victim to certain adversarial attacks. For example, there are false flag attacks where people are able to modify inputs in order to trick ML models, which commonly happens with fooling image classifiers. Additionally, there are things like reverse engineering attacks or membership inference attacks, both attacks that attack the very model architecture, proprietary more often than not, in order to figure out what the architecture is or learn to do exactly the same task as that architecture. The other issue is transparency and accountability. One of the largest problems in machine learning, especially as it's used in these sensitive fields, is that most machine learning models, especially those that use deep learning, lack any sort of explainability or any way of seeing inside the model to know what it's thinking and why it makes the decisions. For example, AI is nowadays used to review resumes and make hiring decisions without any real clear reasoning as to why it believes that these candidates might be good. Of course, in improving transparency, there have been large improvements in explainable AI, with techniques like shapely additive explanations to help interpret model decisions. There are also a variety of different kind of schemas or structures around which models are being structured, especially in the medical field, that are used to make the decisions much more explainable and understandable from a human point of view. Also, systems usually involve humans in the loop, so most models will end up being aids in certain decision-making processes, with a human overseeing those decisions or advice that's given by the models, as opposed to the models themselves being the sole decision maker. The other glaring issue is the environmental impact, especially nowadays with large language models such as GPT-4 and DALL-E, which contain billions, hundreds of billions to trillions of hundreds of billions to trillions of parameters, consume significant amounts of computational power and computational resources. For example, training GPT-3 alone required 1,287 megawatt hours, which is equivalent to more than 100 US households' yearly energy use, which is pretty insane. And of course, the need for advancement in more sustainable AI using energy-efficient architectures and optimizing algorithms to reduce computation is undoubtedly more important than ever.
So now that we talked a little bit about the basics of machine learning, we're going to spend some time walking through this interactive notebook that we've curated for you. It'll take you through the three models that we discussed earlier, so linear regression, decision trees, and neural networks. And hopefully this will give you guys a better idea of how to work with the machine learning model so that when you go and implement one by yourself, you have an easier time setting it up and fine-tuning it and going through the entire process.
To start off our machine learning notebook, we're going to be implementing one of the simplest machine learning models you can implement, the linear regression. The idea behind the linear regression is just fitting a line to estimate y given x, using the equation y equals mx plus b. Of course, in our case, we're only going to be using a single variable to do this, which is we are going to be predicting petal width based on petal length from the iris dataset, which we used in our last module. And our steps are to first train the linear regression model from sklearn, which is a package that contains a lot of useful machine learning utilities and models, and then evaluate the model performance based on R squared and just visually by graphing the data. As you can see on the right, we have some of the data graphed. We'll graph our line as well with that data. Of course, most of the time, linear regressions will have several variables involved. In this case, of course, we're only just using one.
The second model we're going to be looking at is a decision tree. For those of you that are not familiar with what a tree is a data structure that has one root node, which is the starting node, and then all the other nodes kind of branch off from there. A really easy way to think about it is that there's a starting node and that there's two ways you can go, left or right, and there are more data values or nodes at either side. The way that a decision tree works is that it takes a series of binary steps and decisions and recursively understands the thresholds that you can see in this output here. The screenshot is what you're going to get from your notebook after running the cell, and it pretty much just shows what steps the decision tree took to classify the data. We're going to use it to classify the iris dataset based off of different feature values, and there's going to be three main steps that we take. The first is we're going to train our actual decision tree classifier. We're going to look at a neat little function called train test split. Then we're going to visualize the tree structure from there and then evaluate the performance as its whole.
To end off our notebook, we're going to be introducing you to the almighty PyTorch library, which contains a lot of utilities for training neural networks. While neural networks seem complicated, the PyTorch library abstracts a lot of the difficulties of implementing them away from us and allows us to be pretty relaxed when making them and use very simple code in order to train them. Of course, once we've done this, we'll also discuss some of the important differences between these three different models, as well as looking at the performance across all three on the dataset. So to kick off our dataset, we're just going to get right into implementing linear regression. The first thing, of course, we need to do is load the iris dataset, which we'll be using again. It's the same dataset that we use in Module 0. So we'll just do this. Of course, this is pretty much exactly the same code as your Module 0 notebook, so if you guys just want to copy that over, that's also fine too. No reason not to. That should settle that. Run it. And just to show that our data frame loaded correctly, we'll just quickly show the data frame by just putting df in a cell. Of course, now we can plot the data using some code, again, that we would have written in Module 0. And you can see we have our petal width and petal length graph here, which we also showed in our presentation. Now to get started, we're going to be using the sklearn linear regression model, which sklearn pretty much just provides an entirety from start to finish in terms of just constructing the model, its parameters, and training it on a certain data set. So we'll quickly just instantiate the model itself. No arguments need to be passed. If you want to see the documentation for what arguments can be passed, you can also see that. Quickly, we'll also define what our x and y things are, or variables, sorry. Cast these to numpy and then quickly reshape to actually fit the outputs that we want for... wait, I've made a typo here. So this... And then finally, to actually fit our model, we simply just call fit with our x and our y series, which in this case are just big numpy arrays that we've taken from our PD data frame, as you can see. These, of course, just need to be reshaped because sklearn expects them in a certain shape. I think this is just a 90-degree rotation, if I'm not mistaken. So that pretty simply makes things work. And then to get some of the parameters from our model, we can just do this. These, of course, are just indexing into certain parameters that the sklearn object stores itself. So we can always just access those whenever we want to by doing this. And then we have our coefficient and intercept for printing. So we'll just run the cell, and that should fit our model with our model coefficient here and our model intercept here. And then a graph of our model can be shown down here. To score the model, we just use the R-squared score, which is the Pearson's correlation coefficient. It is related to just kind of the correlation between x and y and how well they fit in the model, given the model that we actually have. And if we run this, we get about 93%, which is actually really good. The closer this value is to 1, the better our model actually fits the data. Also, another important note, in this case, we haven't actually split up our data, and we'll get to this later when we're talking about decision trees. But usually what you'll want to do is split your data into a train split and a test split, so that you can see how your model extrapolates to data that it hasn't seen before or hasn't learned on before. Of course, below this, we have a little segment where you can implement your own linear regression, so you can go and do that after this. Another important thing to talk about, however, is how linear regressions actually learn. So in order to learn, a linear regression essentially does math. This equation here is what's known as the residual sum of squares. Essentially, we just take the difference between the value that the linear regression estimates, given its parameters, as well as the actual y value that we want the linear regression to output. We then take a square because not only does that make all the values positive, it also means that we punish much higher differences or much larger errors that the model makes. Essentially, if you have a very large error, squaring it makes that error much, much larger. Whereas if you have smaller errors, it's not so bad. Essentially, the idea is that if the model is really, really far off, we want to push it really, really hard in order to get it into a corrected state. So what this actually means is that we can convert this equation into this, where we have w times xi plus b, xi being some kind of sample or some set of features corresponding to a specific sample, and w being the model coefficient, which we of course have above here, and b being the model intercept, just by the equation y equals mx plus b for a regular linear equation. Now, what's interesting about this is this means that we have an equation that directly relates our parameters of the model to the loss, or how bad or well the model does, the error in a sense. And what that means is that by using the gradient, or by using the derivative, we can actually adjust those parameters in order to get closer and closer to a better solution for fitting our parameters to the specific x and y values that we have. And that's how these machines learn. It's an entirely numerical or mathematical process. So what's important about this is that AI decision makers anywhere in the real world, especially those that use machine learning or deep learning, or even algorithmic ones, ultimately don't have a certain level of intelligence. It's, of course, an emergent property of them having a lot of parameters, but at the end of the day, all of these things come down to just math functions. And that's something that's really important to consider when we're thinking about how AI plays a role in decision making.
Ryan did a quick activity about linear regression, and I'm going to take the next few minutes to do a quick activity about decision trees. Just to reiterate, decision trees are another form of machine learning that make binary decisions to classify data, and we're going to do the same activity except on the iris dataset. The first thing we want to do is extract some key information, with that being the numerical values and then the corresponding categorical labels. The way that we can get the numerical values is by calling our data frame that we instantiated earlier, and then dropping the species labels so that the only thing that we're left with is all of the numerical values. Now, on the contrary, we also want the corresponding categorical labels, and the way that we can do that is we can just simply extract all of the categorical labels that correspond to all of these values. Perfect. Now what we want to do is that we want to split our data into training and test data. The main thing that I want you guys to understand is that we are not going to be testing our data on the same data frame that we trained on. That's an incorrect way of doing machine learning. What we want is we want some training data, and then we want to test our model on the test data to see how well it did. There's a very neat function that we can use here called train test split. It's one of the foundational functions that a lot of people use for machine learning and AI work in general, and it makes the whole splitting process a lot easier. The way that we can do this is we can call train test split with the features and the labels that we have just declared. We'll set a test size and then also extract specific values for the training data and specific categorical values for the X test and the Y test. The way this is going to work is that we can first call xtrain. Python is neat in that we can declare multiple variables on the same line. Then we can call xtest. Now we can do ytrain and ytest. Again, each of these variables correspond to different parts of the data set that we're extracting. Then from there, we can simply call our train test split function. And over here, we're going to pass in our numerical values, the corresponding categorical labels. And then also, we can set an arbitrary test size. It doesn't really matter what you choose, but just for this activity, we'll set it to 0.33. And then in order to make our results more reproducible, this is set by default, but I'm just doing it to show you guys. We can set random state to 42. Now from here, we are going to instantiate our decision tree. This is also a very straightforward process. We can call our decision tree CLF, and then call the tree library, and then specifically call our decision tree classifier function. So now that we have our decision tree classifier function, we want to train our decision tree. We want to give it the data that it's going to learn from. And the way that we're going to do this is that we're going to take our corresponding features and labels that we extracted from the train test split and use that to train our decision tree. So we're going to do CLF is equal to CLF.fit. And the way that we're going to do this is first we're going to give it the numerical values, which is the xtrain. And then we also want to give it the categorical labels that correspond to the xtrain values. And that's going to be stored in ytrain. So from here, we're going to run our cell. Cool. So as you can see, our cell has successfully ran. And now what we want to do is we want to see how well our model is actually trained. So the best way to do this is to
get a score for our decision tree, and we want to test it on samples that it didn't learn on to see how well it's actually performing. This gives us a better intuition as to how well the model applies the distribution as a whole, and gives us a better idea on how the model was trained and what things we can improve on. The best way to do this is we can get our predictions by simply doing clf.predict. This will predict based off of the test data, and then we can get a numerical score to see how well it actually did. Now, by default, clf.score does call the predict function, but just to show you guys a little bit more in depth about how exactly it works, I also store the predictions as well. So what this is going to do is it's going to predict based off the X test data, then compare the results to the Y test data and see how well it actually did. Now we can print out all of these variables to see how well we actually did. So the first thing we're going to do is print out the model accuracy. And that is going to be our score. Then after that, we are going to print out what the actual predictions were that we stored in the predictions variable. And then last but not least, we are going to see what the actual ground truth was, which is pretty much our Y test, which is what we're comparing it to. So if we run this, you can see that our model accuracy is 0.98, so it performed very well. The predictions were also quite similar to the ground truth. In general, our model is performing very well. Now, if we want to actually see what decisions it made and what in general the process was in building this decision tree, we can simply plot the tree. And this will give us a visual representation of the decisions that our model made in order to get to the solution that you see above. Again, this is a very straightforward process. We can simply call the function plot tree on our CLF. And then in order to avoid all of the extra information that comes, we can add a print statement. And if I run this, you can see that we get a visual representation of what the decision tree looks like. Again, there are binary decisions being made on each cell based off of thresholds that were set. And it learns these thresholds over time and then comes to the solution that you guys saw above. One thing to note here is that in the case of linear regression, as Ryan showed, and decision tree, which we just went through, we can see very easily and tangibly the parameters that kind of guided the decisions of the model. But this isn't exactly the case with all machine learning models, as you're going to see in the next activity when we look at neural networks with Ryan.
So now moving on to the multi-layer neural network, otherwise known as a multi-layer perceptron, a neural network, or a feed-forward neural network. Regardless of the name and however complicated they may sound, these neural networks aren't really very complicated, so to speak. You can see here an example of a neural network where we have a set of neurons, each connected with some set of parameters. We have Wi and Bi, which represent a weight and a bias, as they're called, but realistically are just the coefficient and the intercept used for a linear relationship. So essentially what happens is as numbers are being passed through the network, for any two nodes in two different layers, they have some connection between them with some parameters associated with them, and it's just a linear relationship between all of the nodes between two layers. And you tune the Wi and Bi parameters in a fashion not too dissimilar from what we looked at in linear regression until you get the desired outputs in your final output layer. Of course, we don't need to do any of this math really ourselves, because we're going to be using the very powerful PyTorch library, which implements many utilities for constructing, training, and evaluating these things in sequential fashion and just very, very syntactically simple ways. We will use this neural network, of course, to do classification, just as we did with the decision tree, on the iris dataset using pretty much exactly the same features. This does require a lot more code and setup, so I won't be typing out too much because there is a lot to go over. But hopefully you guys get a good understanding of how to use the torch library. So here we have some simple imports, torch, torch.nn, and torch.optim. Optim is where we'll be getting our optimizers and otherwise from. And then torch.nn just has a lot of the neural network utilities and classes inside. So to start, we're just going to set our manual seed. This is for reproducibility reasons. This essentially just gives a seed to the random number generation that Torch uses, which means that every time you run this, we get basically the same results because everything that's randomized will end up being the same. So we also start with defining a model. We'll call this just my model. That derives from the nn.module. This is just a way for Torch to register and know that this is a model with parameters that has a gradient, and to know what methods we should be overriding for it, as well as what to do with it when we're actually using it in training setting. So we'll call the superconstructor in init. Init just initializes the object, and the superconstructor basically just calls the init of the superclass, which is just nn.module. And we'll just call it with the type of module just to register it for Torch's sake. Now to start, we're going to declare some of our layers. Now you'll see here it says FC1. This just means fully connected one. As you can see in the diagram that we have above, the two layers are fully connected because for any two nodes in the two different layers, there's a connection, hence the name fully connected. And each one is a linear relationship. So of course these are going to be torch.nn.linear layers. The two arguments that we passed here is the input layer size and the output layer size. So essentially this will become a matrix of size 4 by 128. And then the same goes for self.fc2 and self.fc3. These are all the linear layers that we have. One is our input layer. FC2 is our hidden layer, which is just of size 128. And then FC3 is our output layer going from 128 to 3. And 3, of course, is important to talk about here because that's how we are going to distinguish classes. We use a method called one-hot encoding, where each class is represented by a vector of size 3. Essentially, the index of whatever class the vector should correspond to is just set to 1. So there's only one index that's actually hot at any point corresponding to the vector. This is very often used for classification with neural networks, and we'll have to do some conversion on our labels in order to do this, but ultimately you'll see that it works out. Now, the other important part of neural networks is activation functions. Between each layer, we put an activation function because otherwise all we have is a bunch of linear layers. When we do backpropagation, because all we're doing is doing derivatives or gradients, if we only have linear relationships between each of the layer, we've essentially just created a more complicated linear regression, and we're not really creating any complexity in the parameters or structure of our neural network. So realistically, without activation functions and that kind of non-linearity, you lose a lot of the nuance that a neural network can pick up on. So in this case, we have two different functions. We have the rectified linear unit, which sounds complicated. Really, it's just a linear function, except if the number is less than 0, we just call it 0. And then the second is a softmax function. This one just converts a value in a set of values into just a probability, essentially a number between 0 and 1, such that the sum of all the values in that vector are equal to 1. So now that we've declared everything in our init function, all we need to do is override the forward function, which is just what happens when the model is given a number and told to do a computation on that number. So we'll take in our input x, we will apply fc1 to x, which essentially just does the matrix multiplication corresponding to going or passing forward on that layer. Then we'll apply relu1, which is our activation function for that layer. Same with fc2, same with relu2, same with fc3. And then finally, we'll apply our softmax to get our probabilities for each of the three classes in our one-hot encoded vector. Now, moving on to our data, there is a little bit of conversion we need to do, as I spoke about, in order to turn this into a one-hot encoded vector. This pretty much just makes a torch set of just a vector of size 3 with all zeros, and based on the number of the class that we see in our original Y train, we'll just set that index to 1 in the vector, and then just append it here. This will just turn it back or overwrite our original Y train and just turn it into a set of those one-hot encoded vector labels. Then the other important part we'll do here is split it in our train dataset, our original train dataset that we already made when splitting into train and test, into a split between train and validation. The reason we'll use validation you'll see soon, but it's just another test set that we use during our training in order to ensure that our model is still able to extrapolate outside of its trained dataset and isn't fitting too much to the trained dataset. Finally, we just convert the train values to PyTorch tensors. Note that we don't need to do this for the labels because we already made them into torch tensors by making torch zeros and stacking them. So this conversion just takes the original NumPy arrays and turns them into torch tensors, which Torch will use for its computations. Now, to begin our setup for training, training seems very, very complicated, and this seems like it would probably be really messy to code, but I'll break it down step by step, and what you'll see is that it's not actually as complicated as one would think. When training, what we do is we set a certain number of epochs, which is how many iterations do we want to train the given model on this data set. The second is a batch size. What batch size tells us, batch size tells us essentially is in each epoch, how many times do we want to run the model and backpropagate on data, or before we backpropagate on the accumulated kind of loss or gradient, so to speak. How many times, how many samples do we want to see before we adjust the parameters of the model? The third thing is learning rate. Learning rate, as we know with the process of backpropagation, just tells us how much of a step or change do we want to make to the actual parameters of the model. If our learning rate is really high, then what we end up doing is making really big changes in our parameters. If it's small, we end up making much smaller changes. Now, of course, this can be kind of important when we're thinking about minimizing the loss function, because if our learning rate is too high, we could miss the minima and then just miss it again every time we go about. And then we never end up actually getting to a really low value of loss because we just miss it every time. However, if it's too low, it'll take forever to actually get to a low value of loss. So there's not really, that will just be more expensive, more computationally expensive, and overall worse. Now, the other thing we need to do, and this is something we do because we're not using a Torch data loader, which we'll get into later, is using batches. Batches, of course, are just, as we spoke about, we have a certain batch size. We have these small groups of the data set that we use to backpropagate on. And this is just kind of calculating the number of batches per epoch, or the number of batches that are in the data so that we know how to feed it in our loop. So now we'll declare our model, make an instance of it. Our criterion here is binary cross entropy. It calculates entropy between the target distribution and the target label and the predicted label. If you guys want to look into that, of course, Torch has really good documentation for it, but it is kind of complicated, so I won't be getting into it too much. Then we have optimizer. We are using the Atom optimizer from the Optim library. This, of course, just requires us to point it to the model's parameters and give it a learning rate. Atom stands for adaptive momentum. Essentially, what this will do is, given our learning rate, it will kind of start to shift the speed at which it wants to adjust based on either how many epochs it's been, how low the loss already is, and several other factors. The idea being that we kind of dynamically adjust how fast we're changing so that we don't end up falling into those patterns of either missing the minima or not approaching it fast enough. Now, starting our training loop, we have for epoch and range number epochs, which just means for the number of epochs we actually specified this to run. We'll print out our epoch, set our model into train mode, so you can set it into train or eval, and essentially that'll tell PyTorch whether or not it should care about gradients. Then for each batch in the our train dataset, which is essentially what we do here, we will calculate our start and end indices of the batch. We will then slice our train data in order to get the train batch and label batch, which is just the specific batch of data we want to work with for that for that iteration. And then we produce outputs from the model by putting train batch into it. Then we'll take loss is equal to criterion, which again is our BCE loss between the outputs and the label batch. We'll do optimizer.zeroGrad to reset the gradients or adjustment that it wants to make, recalculate our loss or do the backward pass with our loss, and then step, which adjusts the parameters of our model. And then finally, we'll do this for all the batches that we have in our X-train, and that's dependent on our batch size. And then we'll finally append to train history, which is just something we'll use later, and print out some information on our training loss. And then finally, our validation step, which is the important part of why we needed to split our data earlier. We set our model into eval mode, which means Torch should not care about the whatever information on gradients or adjustments we want here. And then with torch.nograd, which is, again, just a second safety measure to make sure Torch really does not try to get the model to learn on the validation data set, we will then do basically the same thing we did with our trained data, except on our validation data. And then just append that to validation history and check our validation loss. Now to run the code that we actually have here, very quickly I have my data set and everything set up. So I'll run this, ensure that my imports go smoothly and that my model is declared correctly. And now finally I will run this cell, which will do training. Of course, this training is pretty fast because we only have 4 features. We don't really have too much computation to do. But as you'll see later, computation is pretty expensive and difficult, especially when your data gets really messy, complicated, or large. And so our training completes with very, very, very low losses. As a matter of fact, it's going to be kind of important for us generally to plot our losses and see how they progress. You can see we get this nice curve as it starts to get into a really low score of where essentially we're at basically the minimum really correctness that we can get to. Now, the one thing that you'll sometimes see in other machine learning models or with other data sets, and something we probably won't see here because of the simplicity of this data set, is that our validation loss will sometimes diverge from our training loss. This is a phenomenon known as overfit, and it's the reason why we want our validation loss to actually be something we measure while training. Because we want to see if the model is getting too good at, or too specific rather, for its training data set. Because if it is, then that means that it's not going to do well when we actually use it in the real world. Now, a couple other things we can do is we can now look at the raw accuracy of the model here. And as you can see, our model accuracy is 100% because, of course, if our losses is slow and our data sets is simple, you're going to get pretty much just that. We can also print the predictions, which will be quite a mess because, it doesn't look so great. Now, another thing that might be interesting to think about, and something that we had spoken about earlier, which I will now demonstrate, is this idea of black box functions or black box inference methods. Now, when you think about the decision tree or the linear regression that we had, just think about how simple it was to interpret the results there. With our decision tree and the decision tree graph, we had a very simple way of seeing the decisions that the model took in order to get to its final solution. With the linear regression, as a matter of fact, we had a coefficient and an intercept that the model had come upon that it thought accurately predicted the overall outcomes based on the input value. In this case, we have no clue what this means. What the model has understood from the data and what it uses to actually make inferences on it is entirely alien and ununderstandable to us. So when we use this to make decisions, how can we necessarily justify the decisions that are made, even to ourselves? We know that the machine learning model is, accurate, of course, but even then, in the cases when it's not, we don't really have a way to know for certain, nor do we really have any way to know why it made the decision it did. So this is something interesting to think about, especially when it comes to ethics and machine learning, and something will definitely come up later in the course. Now, another thing to talk about, especially when it comes to accuracy, is that while accuracy is a decent metric, we often prefer metrics known as precision and recall. So you can see the two questions here of what define precision and recall. They're very closely tied to our true positive and false negative rates. Essentially, the idea of recall is, out of all the true samples, how many did we correctly identify as true? Which you can see here, the true positives over all positive samples. And then for precision, we can define that by the question, out of all the samples that we call true, how many were actually true? Which is, in a sense, our false positive rate. So we'll leave the calculation of these two to you guys, but you can see that these two metrics would be important, especially when thinking about what is the risk associated with our false positives and what is the risk associated with our false negatives. Because if we were to say that someone, say in the case of disease diagnostics, if we were to say that someone has a disease and needs very invasive life-altering surgery, is that worse than telling them they don't have the disease and they don't have that massive life-altering surgery? I think this is the case in things surgeries that require hysterectomies for cases of cancer, especially in the abdomen. This was like one example I've seen definitely out in the world. So these metrics are generally much better for describing the performance of the model, and will usually be grouped under something called receiver operating characteristics. Of course, we'll leave the calculation of these values as well as the exploration of them to you guys. The other thing that a lot of machine learning researchers use is the F1 score, which is kind of a conglomerate of the two metrics, and just tells us a lot more about how the model is performing, as opposed to just raw accuracy. Of course, in the previous module, we had that example of a model that just predicted everyone living in Seattle because most of the people in its trained data set lived in Seattle. And there are a lot of problems in the real world where you get data sets like this, where there's only a really small minority of the data set that actually is a positive case for whatever the label might be. So generally in those cases, precision and recall act as much better metrics than just raw accuracy, even though raw accuracy at times can be useful.
So that brings us to the end of our module where we covered the intro to machine learning, learn about some basics, and we hope that you guys had a fun time getting an introduction to these topics and also doing the interactive activities.
Just to summarize everything that we did, we went over some basic machine learning models such as the linear regression, the decision tree, and the multi-layer perceptron. We went over comparing these three different models as decision-making agents in the real world, and how explainability of their answers, as we saw in the linear regression decision tree, we had explainable answers, but for the MLP we didn't. How important that is to the ethics of using them in decision-making processes. We also looked at some different metrics for assessing model performance, aside from just accuracy, and also weighed the benefits and disadvantages of using those metrics.
Looking forward, we're going to be working with some more hands-on ethical implication work. We're going to be exploring privacy, security, and just data in general in our next module. And we're going to be working with a lot of cool libraries, so we hope to see you there. Thank you.